The Coandă effect is the tendency of a fluid jet to stay attached to a convex surface. The principle was named after Romanian aerodynamics pioneer Henri Coandă, who was the first to recognize the practical application of the phenomenon in aircraft development. Discovery. An early description of this phenomenon was provided by Thomas Young in a lecture given to the Royal Society in 1800. The lateral pressure which urges the flame of a candle towards the stream of air from a blowpipe is probably exactly similar to that pressure which rises the inflection of a current of air near an obstacle. Mark the dimple which a slender stream of air makes on the surface of water. Bring a convex body into contact with the side of the stream. In the place of the dimple will immediately show the current is deflected towards the body, and if the body be at liberty to move in every direction it will be urged towards the current. 100 years later, Henri Coandă identified an application of the effect during experiments with his Coandă 1910 aircraft, which mounted an unusual engine he designed. The motor-driven turbine pushed hot air rearward, and Coandă noticed that the airflow was attracted to nearby surfaces. He discussed this matter with leading aerodynamicist Theodor von Karman, who named it the Coandă effect. In 1934, Coandă obtained a patent in France for a method and apparatus for deviation of a fluid into another fluid. The effect was described as the deviation of a plane jet of a fluid that penetrates another fluid in the vicinity of a convex wall. Applications. The Coandă effect has important applications in various high-lift devices on aircraft, where air moving over the wing can be bent down towards the ground using flaps and a jet sheet blowing over the curved surface of the top of the wing. The bending of the flow results in aerodynamic lift. The flow from a high-speed jet engine mounted in a pod over the wing produces increased lift by dramatically increasing the velocity gradient in the shear flow in the boundary layer. In this velocity gradient, particles are blown away from the surface, thus lowering the pressure there. Closely following the work of Coandă on applications of his research, and in particular the work on his aerodynamic, John Frost of Avro, Canada also spent considerable time researching the effect, leading to a series of inside-out hovercraft-like aircraft from which the air exited in a ring around the outside of the aircraft and was directed by being attached to a flap-like ring. This is as opposed to a traditional hovercraft design, in which the air is blown into a central area, the plenum, and directed down with the use of a fabric skirt. Only one of Frost's designs was ever built, the Avrocar. The VZ-9AV Avrocar was a Canadian vertical takeoff and landing aircraft developed by Avro Aircraft Limited, as part of a secret United States military project carried out in the early years of the Cold War. The Avrocar intended to exploit the Coandă effect to provide lift and thrust from a single turbo-rotor, blowing exhaust out the rim of the disc-shaped aircraft to provide anticipated VTOL-like performance. In the air, it would have resembled a flying saucer. Two prototypes were built as proof-of-concept test vehicles for a more advanced USAF fighter and also for a U.S. Army tactical combat aircraft requirement. Avro's 1956 Project 1794 for the U.S. military designed a larger-scale flying saucer based on the Coandă effect and intended to reach speeds between Mach 3 and Mach 4. Project documents remained classified until 2012. The effect was also implemented during the U.S. Air Force's AMST project. Several aircraft, notably the Boeing YC-14, NASA's quiet short-haul research aircraft, and NAL's ASCA research aircraft have been built to take advantage of this effect, by mounting turbofans on the top of the wings to provide high-speed air even at low flying speeds. but to date only one aircraft has gone into production using this system to a major degree, the Antonov An-72 Kola. The Shinmiwa US-1A flying boat utilizes a similar system, only it directs the prop wash from its 4 turboprop engines over the top of the wing to generate low-speed lift. More uniquely, it incorporates a 5th turboshaft engine inside of the wing center section solely to provide air for powerful blown flaps. The addition of these two systems gives the aircraft an impressive STOL capability. The McDonnell Douglas YC-15 and its successor, the Boeing C-17 Globemaster III, also employ the effect. The Notar helicopter replaces the conventional propeller tail rotor with a Coandă effect tail. An important practical use of the Coandă effect is for inclined hydropower screens, which separate debris, fish, etc., otherwise in the input flow to the turbines. Due to the slope, the debris falls from the screens without mechanical clearing, and due to the wires of the screen optimizing the Coandă effect, the water flows over the screen to the penstocks, leading the water to the turbines. The Coandă effect is used in dual-pattern fluid dispensers in automobile windshield washes. The operation principle of oscillatory flow meters also relies on the Coandă phenomenon. The incoming liquid enters a chamber that contains 2 islands. Due to the Coandă effect, the main stream splits up and goes under one of the islands. This flow then feeds itself back into the main stream, making it split up again, but in the direction of the second aisle. This process repeats itself as long as the liquid circulates the chamber, resulting in a self-induced oscillation that is directly proportional to the velocity of the liquid and consequently the volume of substance flowing through the meter. A sensor picks up the frequency of this oscillation and transforms it into an analog signal yielding volume passing through. In air conditioning, the Coandă effect is exploited to increase the throw of a ceiling-mounted diffuser. Because the Coandă effect causes air discharged from the diffuser to stick to the ceiling, it travels farther before dropping for the same discharge velocity than it would if the diffuser was mounted in free air, without the neighboring ceiling. Linear diffusers and slot diffusers that present a greater length of contact with the ceiling exhibit a greater Coandă effect. In cardiovascular medicine, the Coandă effect accounts for the separate streams of blood in the fetal right atrium. It also explains why eccentric mitral regurgitation jets are attracted and dispersed along adjacent left atrial wall surfaces. This is clinically relevant because the visual area of these eccentric wall-hugging jets is often underestimated compared to the more readily apparent central jets. In these cases, volumetric methods such as the proximal isovelocity surface area method are preferred to quantify the severity of mitral regurgitation. In medicine, the Coandă effect is used in ventilators. In meteorology, the Coandă effect theory has also been applied to some air streams flowing out of mountain ranges such as the Carpathian Mountains and Transylvanian Alps, where effects on agriculture and vegetation have been noted. It also appears to be an effect in the Rhone Valley in France and near Big Delta in Alaska. In Formula One automobile racing, the Coandă effect has been exploited by the McLaren, Sauber, Ferrari and Lotus teams, after the first introduction by Adrian Newey in 2011. To help redirect exhaust gases to run through the rear diffuser with the intention of increasing downforce at the rear of the car. Due to changes in regulations set in place by the FIA from the beginning of the 2014 Formula One season, the intention of redirecting exhaust gases to use the Coandă effect have been negated, due to the mandatory requirement that the car exhaust must not have bodywork directly behind the exit for use of aerodynamic effect. Demonstration. The Coandă effect can be demonstrated by directing a small jet of air upwards at an angle over a ping-pong ball. The jet is drawn to and follows the upper surface of the ball, curving around it, due to the acceleration of the air around the ball. With enough airflow, this change in momentum is balanced by the equal and opposite force on the ball supporting its weight. This demonstration can be performed using a vacuum cleaner if the outlet can be attached to the pipe and aimed upwards at an angle. A common misconception is that Coandă effect is demonstrated when a stream of tap water flows over the back of a spoon held lightly in the stream the spoon is pulled into the stream. While the flow looks very similar to the airflow over the ping-pong ball above, the cause is not really the Coandă effect. Here, because it is a flow of water into air, there is little entrainment of the surrounding fluid into the jet. This particular demonstration is dominated by surface tension. Another demonstration is to direct the airflow from, e.g., a vacuum cleaner operating in reverse, tangentially passed around the cylinder. A wastebasket works well. The airflow seems to wrap around the cylinder and can be detected at more than 180 degrees from the incoming flow. Under the right conditions, flow rate, weight of the cylinder, smoothness of the surface it sits on, the cylinder will actually move. Note that the cylinder will not move directly into the flow as a misapplication of the Bernoulli effect would predict, but at a diagonal. The effect can also be seen by placing a can in front of a lit candle. If one blows directly at the can, the air will bend around it and extinguish the candle. Problems caused. The engineering use of Coandă effect has disadvantages as well as advantages. In marine propulsion, the efficiency of a propeller or thruster can be severely curtailed by the Coandă effect. The force on the vessel generated by a propeller is a function of the speed, volume and direction of the water jet leaving the propeller. Under certain conditions, the Coandă effect changes the direction of a propeller jet, causing it to follow the shape of the ship's hull. The side force from a tunnel thruster at the bow of a ship decreases rapidly with forward speed. The side thrust may completely disappear at speeds above about 3 knots.